Welcome, everybody, to the Arizona Geological Society's September evening presentation. Let me introduce Tim Marsh very quickly to you. Dr. Marsh has a 30-year career in mine geology and exploration with a focus on porphyry copper deposits. He's the former chief geologist of Resolution Copper Company, formerly of Rio Tinto Company, where he helped drill some of the first deep drill holes into what is now considered to be America's largest copper deposit. Along the way, he's earned a Bachelor of Science in Geological Engineering from the Colorado School of Mines and a PhD from Stanford University in ore deposits and exploration. Tim, I'll go ahead and hand it off to you at this point.
Good. I'll take a second and make sure to recognize Dr. Mansky there, the guy that did a much bigger part of finding Resolution. I helped drill some of the holes into it, but Mansky did the brain work to find the thing, him and Don Hammer, Alex Paul. But I had the honor of getting a look at their discovery, and really it was being told by Rio Tinto that I had the opportunity to grid drill Resolution on 75-meter centers that got me interested in doing something else. And that was looking for the next one rather than spending an entire career drilling 6,000 and 7,000 foot holes on 75-meter centers. So in the early part of 2022, Bell Copper has, in my mind, succeeded in finding a new big porphyry copper deposit, and I hope to convey that tonight, not just by me saying so, but hopefully some of the information I'll be able to share will convince you that we're on to something new and something big. I got to start out with this to satisfy the lawyers. The best way I can summarize it is I am a habitual liar. Everything I'm going to say tonight should be taken with a lot of salt. I'm the guy that Mark Twain tried to warn you about, the liar standing next to a hole in the ground. My holes are usually only a few inches in diameter, but really you can't rely on anything I say to do anything, and especially don't give me any of your money expecting to get it back. The story tonight takes place up in Northwest Arizona on a linear trend of porphyry copper deposits that includes Resolution, includes Baghdad, Mineral Park, and another project that Bell Copper's been working on for a long time that's been renamed Perseverance. I used to call it Kaba after the Kaba mine. But these two projects that Bell Copper now has are sandwiched in between Mineral Park on the northwest and Baghdad on the southeast. So again, northwestern Arizona, Mojave County, Bell has two systems we've been exploring. Perseverance used to be called Kaba, and now Big Sandy. We're in elephant country for sure. 10% of every pound of copper in existence in the world has come out of Arizona in the past about 120 years. There's a lot more we think to be found, and we think we're part of that process. Here's a table of really big porphyry copper deposits. Porphyry copper deposits are one of the biggest reservoirs of metal on Earth. Good things to find. They last a long time. They're big. They got a lot of metal in them. The big ones have been in production for 120 years now. And one way of measuring them is by mapping out the distribution of pyrite. More than any other element that they have in them, it's sulfur that makes them geochemically anomalous. And so just measuring the distribution of pyrite in a system gives you some sense as to how big it might be. Big Sandy, the pyrite shell there is 6 by 5 kilometers. Perseverance 5 by 3 kilometers. And we know that because we can walk around on the bottoms of these deposits. And I would argue that in life, you can judge a lot of things about how good the tops will be if you can get a peek at the bottom. At Big Sandy and Perseverance, they're exposed in the Hualapai Mountains, and they've been known for over 100 years. And geologists have drilled a lot of holes in in both of them. Big Sandy, the root zone there is Diamond Joe, the Diamond Joe Peak area. And Perseverance, the root was known as the Wheeler Wash Porphyry system. They're giant systems, and the guys at University of Arizona mapped them back in the 70s and wrote theses on them. Philip Gurla at Diamond Joe and John Vuich at Wheeler Wash, under the tutelage of Spence Titley and John Gilbert. And they showed that these were big porphyry copper systems, and they drilled and they drilled. The only advice I would have given them if I'd have been around back then was to point your drills up. You're underneath where the copper shell ought to be. The copper shell is up in the air, or was up in the air, where the air is today. And basin and range faulting has shifted the more prospective parts of the system out into the valleys. But by measuring the dimensions of the pyrite shell, we can see that at Diamond Joe and at Wheeler Wash, Big Sandy and Perseverance, the size there argues that you ought to spend some time looking for the tops. And but before I even started working at Resolution, I had the idea of going out in the Big Sandy Valley and looking for the chopped off tops of the Diamond Joe and Wheeler Wash porphyries. You can see by the size of the pyrite shells, they stack up well with the biggest porphyries on Earth. So here, Big Sandy, this is on the east side of the Big Sandy River. If you're driving from Phoenix to Vegas, you drive through Wickiup, about 10 miles north of Wickiup. If you look off to the right, you might see a little bit of evidence that I've been scratching around in the hills there looking for copper. That was Godby Drilling's core rig, a Titan II drill that's now successfully drilled to 6,600 feet for Bell. Little plug there for Godby Drilling. They did a good job for me. So again, by looking at the bottom of these systems, it's pretty clear that the right things have happened. There are laramide intrusions. You see this, you guys seeing, let me see, I'm gonna click that again. You're looking at a map with kind of an aerial photograph with some red outlines on it.
Yep.
You seeing that? Okay. So this outline on the left is the Diamond Joe porphyry, 6 kilometers by 5 kilometers. You can see a fantastic array of radial fractures, concentric fractures, really centered on the apex, the central apex of that intrusion. It's been well dated, well studied. It's been drilled by all kinds of people. Inspiration Copper in the late 50s, Gulf Minerals for a long time in the late 70s into the 80s, and as recently as about 2010 by Freeport back near the Leviathan mine. This area was historically productive for moly. Back in World War I, it produced for hard things that they threw around in World War I from the Leviathan mine. So there's a lot of quartz, there's a lot of potassic alteration, a lot of sericitic alteration, all the things we like to see in porphyry copper deposits, rocks that have been dated at 74 million years, all the right things except for a economic copper shell. And again, if I could have been around when say Gulf was drilling that area, I would have said point the drill up, because we're underneath the copper shell. We need to get to some point in the system that's a few kilometers shallower. Because of basin and range faulting, that location is somewhere off to the east under gravel. When I started getting some confirmation by drilling further north up around the Cabo mine area that this model was kind of working out, I took a stab early on, a little too close to the range front fault, drilled some deep holes, never got out of gravel, went 3,000 and 4,000 feet in gravel. Didn't find anything resembling bedrock, but I saw some porphyry altered fragments and some native copper. That effort met with failure after we didn't have enough money to keep the claims paid for, but the idea stayed firmly in mind. Interestingly, in 1980, The NURI program, Department of Energy and USGS went out and drilled a 5,000-foot hole a little further east of where I drilled. They also never got down to bedrock, but I don't think they did it, but I've panned the cuttings from that hole and there's native copper in those cuttings. So there's a large patch of fill out in that valley that's got native copper floating around in the gravel, and that kept me interested. In 20, let's see, the system we've got up to the north, we call it Perseverance now. It's under option to a Robert Friedland company, Cordoba Minerals, who has done a little bit of work there. They helped us drill one of our last holes, and they've subsequently drilled another hole, but the pace of play was intolerably slow. Them working on our project, so I got impatient and I said, well, let's go try the next one to the south again. But that was guided by new information that previous joint venture partner Rio Tinto on the Perseverance project had showed us that there were chargeable electrically conductive rocks much further out into the valley than I would ever have guessed. And so that allowed me to be a little more bold about how far the hanging wall of that Wallapai fault might have slipped. And Bell in early 2020 began staking on the east side of Highway 93 and even on the east side of the Big Sandy River to try and find that decapitated top. We staked 260 claims, picked up some state mineral exploration permits. As we got out on that ground and began looking at the gravel, you actually see exotic copper bubbling up the faults that cut the gravel in quite a few places. You find transported copper-bearing fragments in some of the more distal fanglomerate clasts on the east. It became pretty clear there were things in that gravel that just weren't represented by what's available back in the footwall, much higher grade copper-bearing minerals, all types of quartz veining, biatitic alteration, just things that you like to see in a good porphyry copper deposit that were present in the gravel on the east side of the valley that just weren't represented back there in the footwall. So it was clear that there was some source for the gravels on the east that really supported the idea that a more copper-rich top to this system existed and was leaking its copper through an active modern groundwater system back up to the modern ground surface, cementing in some places the valley filling gravel. In July of 2020, Bell got Quantec out on the ground, and Quantec ran a magnetotelluric survey. That survey showed a large electrical conductor that was real encouraging. Well, they showed it probably cresting at about 400 meters below surface. We haven't found that shallow spot yet by drilling, but we started drilling the north side of that anomaly with our first hole. And after about 900 meters of gravel, we broke into a porphyry system, looked like a fine-grained granodiorite porphyry. BS1, our first hole, cut that system somewhere near the inside edge of the propylitic environment. And that location is about 13 kilometers east-northeast from the Diamond Joe stock. So we moved a long ways out into the valley, drilled blind through nearly 900 meters of gravel. And underneath that gravel were rewarded with rocks that had quartz veins, molybdenite crystals, chalcocite, a little bit of chalcopyrite, more zinc than I wanted to see, but all the features that are characteristic of a porphyry copper system. These are some of the pieces of evidence. I've changed slides now. You should see some core with native copper on the fractures. Are you seeing that?
Nope.
No. Okay.
There we go.
Got it. Okay. So some of the early drilling showed native copper in the gravel. So that was encouragement that sometime after the gravel was deposited, nature began leaking copper-rich water up through the fractures in the gravel. This is kind of Gila type gravel, 10, probably maximum 15 million years old based on the age of the underlying peach spring tuff and basalt. And I was able to correlate some of the Precambrian class, kind of an aquarius megacrystic granite, finding very similar looking propylitically altered pieces of this Precambrian granite 13 kilometers apart. So I felt I had a slip direction and approximate magnitude fairly well established prior to drilling this hole fairly blindly through gravel. Again, I mentioned exotic copper. That's one of the tells that there's something important in the subsurface at Big Sandy. This funny looking black rock looks like a piece of asphalt, and it is just valley filling gravel that's been cemented by neodicite. This piece runs about 1% copper and about, I don't know, 10% manganese. So it's a manganese copper oxide that glues the gravel together along particular young faults at the elevation of the Big Sandy River. So it's fairly recently in the geologic past, there's been a metal-rich groundwater discharging to surface. It's not happening today, but fairly young sediments that are glued together with this copper, saying that, hey, it's worthwhile getting underneath the gravel and seeing what's producing this copper. This black stuff looks a lot like what you see downstream of Chuquicamata in the Exotica deposit. As we got out on the ground, we began finding mineralized fragments in the fairly young valley filling gravel. You see all the kinds of veins you like to see in porphyry copper deposits, A veins, D veins, forming a particular fan about roughly 1 kilometer on a side. This is far to the east. So it suggested there might be an upthrown block under relatively shallow gravel cover out in the middle of that valley, shedding these mineralized copper-rich fragments. Another thing I like to look at anytime I'm exploring is what sorts of heavy minerals are associated with the gravels. What you find in these gravel deposits are zircons that look like they came out of a laramide porphyry. Not the purple square cross-section zircons you see in a lot of the Precambrian rocks, but more champagne colored, ornately faceted zircons typical of productive laramide porphyries in Arizona. And the angularity of the copper bearing fragments suggested, hey, these things hadn't washed 13 kilometers out of the footwall, that they had formed in a fan much closer to the footwall and been transported to their current location in the hanging wall of a fault. I think the lifetime of a boulder in the bottom of the Colorado River, bouncing down the Colorado River, is about 10 miles. So a boulder that falls off the wall of the canyon, say it's a good Precambrian boulder, doesn't make it much more than 10 miles before it's gone. So these things 13 kilometers out from the range front probably didn't roll there in debris flows. It'd have been pulverized in the process, I would imagine. But it argued for a much more proximal source, and that was enough to get me drilling. We did run this magnetotelluric survey. Quantec ran it, and it showed a very unusually strong electrical conductor. To this day, I can't tell you why that patch of ground is electrically conductive, but its resistivity is on the order of 10 to 15 ohm meters in an area about 2.5 by 2 kilometers, situated adjacent to this copper-bearing fanglomerate. And just the two things seem spatially related enough that I imagined in my wildest dreams that there is a genetic relationship between the two things, this electrical conductor and this pile of porphyry copper fragments. So by, I think it was about October 2020, we got to be drilling up there and started drilling away. So after 900 meters of drilling, we found a core that should be looking at some zircons under a microscope. See if I can make sure where we're looking at here. You seeing uranium lead zircon dating?
Yeah, that's what we're seeing.
All right. So there's a piece of core on the right, semicircular segment of a circle piece of core from about 900 meters down at granodiorite. And then an outcrop to the left of that from the Diamond Joe stock. So our core hole and the Diamond Joe stock are 13 kilometers apart. Over the Christmas of 2020, I picked the zircons out of both of them, sent them up to the University of Idaho for dating, and the ages came back 74.2 and 74.9, both of them plus or minus about 1 million years. So they're indistinguishable in age. So at least permissibly, I had found the top of something the same age as Diamond Joe, which is really what I set out to do, and hopefully with some copper in it. What's also interesting about this dating exercise, the much older zircons that were present with the laramide zircons were roughly the same proportions of old Precambrian 1.4 and 1.6 billion year old Precambrian xenolithic zircons in these samples. So they seem to be rocks that formed permissibly from the same porphyry intrusion. Should be looking at slide 13.
Drilling program, right?
Okay.
Yeah,
so
that's
what we saw in that first intersection, once we got under the oxidation, was chalcocite overprinting pyrite. Down in the lower left, some coarse molybdenite grains. These are about 3 millimeters across, very coarse, real flashy molybdenite grains. I sent those to Holly Stein at Colorado State University. She called back and said, "Tim, you about broke my mass spectrometer." They ended up running 8,700 and 9,300 parts per million rhenium, which is nearly 1% rhenium in the molybdenite. But globally, those are extraordinarily high rhenium numbers. In terms of alteration, the hole was kind of on the inside edge of the green rocks environment. We saw lots of D veins, complexly zoned D veins with sulfide center lines, mainly quartz pyrite, little chalcopyrite, sphalerite center lines. But we weren't quite in the environment I wanted to be in. We moved to the south. Excuse me, I got a cough. We moved to the south 1.6 kilometers off to the other side of the MT anomaly. Again, drilled down into basement through about 650 meters of gravel on our second hole. And we drilled a lot of countertop rock, a lot of old Precambrian granite. It had some real interesting zoned veins with epidote center lines, some barite, a little bit of chalcopyrite on the center lines, but it was pretty clear we weren't in the environment I had dreamed of. So after making sure that we weren't going to hit the porphyry with that hole, we moved to the third hole, 1.2 kilometers west of BS1, our first hole. You can see we're doing very big step outs. I'm fishing blindly through pretty thick cover. And BS3 was a dream come true. So after about 3 months of drilling through gravel, almost 4,000 feet of gravel, we broke out of gravel into this rock, very strongly sericitically altered quartz vein bearing quartzite porphyry. The texture of the porphyry is almost indecipherable. The phenocrysts are essentially obliterated except for the quartz. It's got some quartz eyes in it, but it's really altered to sericite on a very pervasive scale. No sign of epidote, very little to no chlorite. So we had moved considerably into the the inner part of the system. Quite a few quartz veins, but just earthy red hematite, primarily in the first 111 meters of leached cap. So I watched this come out of the ground day after day, about through Thanksgiving of 2021, dreaming what might be causing that hematite. I have an X-ray fluorescence analyzer, which I would hit that hematite with it all the time, and really saw very low copper numbers, 50, 60, 70 parts per million copper in the earthy hematite, but it looked like fertile hematite to me, so we kept drilling. And starting at 1,302 meters, we began seeing chalcocite. The first lick of chalcocite ran over 4% copper, just 30 centimeters, but it was a good slug of chalcocite, showing that the hole needed to keep going. So we drilled eventually 200 meters of supergene enriched chalcocite mineralization. That's chalcocite rimming pyrite. I haven't seen anything that looks like primary chalcocite. And really in that upper 200 meters, chalcocite was the only significant copper bearing mineral. Wasn't any copper oxides, no blues and greens. It just went straight from the earthy red hematite down into chalcocite. And that's my fax machine ringing there in the background. Sorry for that. I'm now looking at slide 17. Tell me when you see it.
It's up.
Yep, it's up.
All right, so assay results, we cut 200 meters between 1,302 and 1,502 meters, averaging 0.42% copper, 8.4 pounds per short ton, along with 2.4 grams of silver. And there was a somewhat richer interval of 54 meters, grading 0.67% copper and 3.7 grams of silver. This chunk of core I'm holding in my hand ran about 2.1% copper, one of the very few intersections or assay intervals that ran over 1% copper. Most of it was just pretty boring, 0.3, 0.4, 0.5% copper, as finely disseminated, just very light peppering of chalcocite. The brassy, shiny veinlet running through there is pyrite that's crisscrossed with late kind of crackle texture, chalcocite veinlets cutting through it. More important is that dark gray vein up above the brassy one. That's just pure chalcocite that's taken out a pyrite vein. So we had, out of that 200 meters, just 3 assays that ran over 1% copper. Down to slide 18. This is a pretty typical picture of the texture, photomicrograph. Field of view, there's about 7 millimeters. The grains of pyrite are roughly a millimeter across, but they've got a dark gray, silver gray rim of chalcocite surrounding the pyrite. It's just a good old supergene enriched chalcocite. You can see the texture of the porphyry is pretty much obliterated. You can make out a quartz eye there, a few quartz eyes. Most of the rest of the porphyry is just, it's muscovite. Now I'm down to slide 19.
Correct.
Once we got out of the supergene chalcocite at about 1,502 meters, I kept going because there were plenty of sulfides in the interval. We drilled about 700 meters from the top of the supergene enrichment down to the bottom of the hole at 2,026 meters, where the pyrite content averaged around 10 weight percent, so maybe 5 volume percent pyrite. That's a lot of pyrite. A lot of cerussite from top to bottom. This drill interval, about 800 meters, is nothing but cerussite, quartz. Very few intervals where you actually see the original texture of the porphyry. Just myriads of D veins, a patch of core, maybe the size of 1 or 2 fists in that 800-meter interval, where you could see kind of caramel brown phlogipitic biotite, pervasive shreddy biotite, but most of that was completely overprinted. If it had been present on a larger scale, it's just completely been overprinted by the sericitic alteration, the pyrite mineralization. The copper that's in that deeper interval below the supergene enrichment is mainly in the form of chalcopyrite, a little bit of tennantite, probably less than 10% of that copper is carried by tennantite, a little bit of sphalerite and trace molybdenite, but really the sulfide of predominance is pyrite over that interval. And that altogether, it tells me I haven't found the place I'm looking for. I want to find that supergene enrichment blanket where it sits right on a copper shell. And I think I need where to be looking for it. That interval of primary mineralization underneath the chalcocite, the 524 meters below 1502, average 0.16% copper, a very monotonous 0.16% copper. It would tick up a couple of tenths or a couple of hundredths and down a couple of hundredths, and 2.2 grams of silver, but overall a pretty monotonous sequence of sericitized porphyry. And in all of BS3, 800 and whatever meters, nothing in there but laramide looking porphyry. I haven't dated anything out of BS3 yet, but there's no Precambrian, nothing but porphyritic rocks that all look about the same, roughly quartz monzonite composition, and kind of a porphyritic aphanitic texture with the usual characters, a few prominent cave bars every now and then. Quartz eyes are present in most of it, and if the alteration hasn't taken out, a little bit of primary biotite, but most of that's been destroyed by sericitic alteration. The average ratio in that deep interval of chalcopyrite, pyrite to chalcopyrite is 20-to-1. It's very, very pyrite dominant. So I didn't get to the place I wanted. You see the piece of core from the bottom of the hole, 6648 feet. Got a lot of pyrite in it. Very sericitized. And as you can tell the way the presentation's going, I don't have the bandwidth to show you a lot more core, but I put about 80 boxes of core into a presentation with the girl from Ipanema as the background music. And I was going to run you for about 5 minutes from top to bottom through BS3 and let you share in the dream that I experienced between about November of 2021 and March of 2022 as we drilled this hole. Each day was a dream come true, seeing this stuff come out of the ground. We've got more to do, but we were seeing the right things. Now, I always knew if I ever got something resembling ore in a core sample, I was going to get it in and make sure it would come out easily. So we sent the assayed interval from BS3 into SGS Lakefield up in Ontario and had froth flotation and acid leach testing done on the chalcocite. Turns out it does pretty good. We recovered 80% of the copper into a concentrate grading 25% copper and 160 grams of silver. So that worked pretty good. Mineralogically, SGS looked at it with their TEMA X system. They say 75% of the copper is in the form of chalcocite, 15% is bornite. I would argue that the bornite is probably idaite, probably a copper iron sulfide that's supergene rather than hypogene in origin. We'll find out, but essentially none of the copper was as an oxide copper mineral. Went straight from earthy hematite down into supergene chalcocite. Quartz and muscovite are the dominant gangue species. Carbonate minerals are very sparse at about 1/10 of a weight percent. And so that opens up the avenue for leaching this stuff with acid without losing acid. Here, the bulk cleaner concentrate on the flotation testing graded 25% copper, 130 grams per ton silver. We lose a bit of the silver in the flotation, but roughly it tracked with the chalcocite. We ran ferric leaching, 30 gram per liter sulfuric acid on ground ore. So this isn't really representative of an in situ process, but we found we could get plus 96% of the copper out by leaching it with sulfuric acid. We also found that the sample itself generated free acid during the leaching process. So we don't have an acid consuming environment. We've got an acid generating environment, which would make it a little more amenable to an in situ idea if the bulk rock will also leach. There was very little molybdenite in the supergene enrichment zone, but I asked SGS to try and make a concentrate. They did pretty good given that they were given a rock that had very little moly in it. They made a concentrate grading 20.7% moly, and they think they could do a lot better if I could actually give them some good molybdenite in the rock. But I really wanted to know what's the rhenium grade. If we move 1.2 kilometers from that nearly 1% rhenium that we saw in BS1, what's the rhenium grade in the molybdenite? And they said, hey, if we could make a 50% concentrate out of what you gave us, it would grade approximately 1,700 grams per ton rhenium, or about 0.17% in a typical molycon grading 50%. So it gives us hope that once we get out into a more moly-rich environment, rhenium will be an economically significant part of what we're finding. Got some TEMA X images of chalcocite grains. This is the stuff I really love. Electron microscope imaging, really thousands of chalcocite grains for our BS3 sample. So you can see mineral associations, and by grinding to minus 100 microns, 80 microns, 40 microns, you get some real nice clean chalcocite grains, and it gives me confidence that with a bit more metallurgical testing, we could make a better concentrate than 25% copper, which isn't good. I think most smelters today would be real happy to be getting a clean chalcocite 25% concentrate. This is the main diluent in the concentrate, and that's clean pyrite grains. It floats just like the chalcocite. SGS spent a little bit of effort trying to suppress the pyrite. They cleaned it up to 25%, but again, the main diluent there is pyrite. Adds some heat to the smelter, keep the smelting process going, but if we could clean it out, that'd be good. But there's really not much else in the concentrate. We're not seeing a lot of zinc, not seeing a lot of arsenic, not seeing relict chalcopyrite grains. Let's see, I'm now down to slide 14.
24?
Yeah, 24. There you go.
Okay.
So this is interesting on me. The red there is pyrite. That second tier of grain images below that is grains that are composite chalcocite and what SGS classified as bornite. If it's bornite, that's pretty interesting. I hypothesize that it might be idaite rather than bornite. But anyhow, there's really not much other than chalcocite, this copper iron sulfide, bornite, or idaite, and pyrite. But it's a pretty nice looking concentrate. A good reason to look for something cleaner. And just about the end of it here. This is what I imagine in the subsurface. Now in slide 25. You seen slide 25 yet?
Yes, 25 is up.
Okay, so here's a cross section down through plus 1 kilometer of Gila type gravel cover.
Nice.
You see off on the right, BS2, the second hole I drilled, it cut a little tertiary basalt, probably 20 million year old basalt, just before going into some pretty dry Precambrian. But again, that Precambrian is cut by veins with some phyllic envelopes, a lot of epidote on center lines of veins, barite mineralization. Then off on the left, BS3, the curvature in that hole is real. That's a gyroscopic survey. If we had put a little Viagra in our mud, maybe we'd have hit that hypothesized supergene enrichment blanket over the primary copper shell with BS3, but it sagged on me. And We got a supergene enriched blanket that I think is hydrologically displaced from the source rock. I don't think the chalcocite that we see in BS3 really came from the underlying primary. I think it was probably remobilized from something a little better just off to the side. And consequently, I'd like to get a hole into that position. That seems pretty close, but it's a 900 meter, more than a half a mile offset from the collar position, and it'll be more than a 500 meter offset down at depth. But I'm looking for a supergene enrichment blanket sitting on top of where the main primary copper shell would have been, with chalcopyrite, maybe some bornite, providing the copper for that primary copper shell. And I'd sure like to be drilling this month. I'm permitted there. I got my road built. I got my pad built, and I'm selling raffle tickets. So get yours today. And remember what I warned you about. If you give me your money, you'll never see it again. All right, and remember back. I'm looking at slide. I don't know. It's the next one. Must be about 26. Huh?
Yeah, 26 landscape side. Yeah, with the drill rig.
Really, the thing that got me out at Big Sandy was the encouragement that we had seen back at Perseverance, or back at our Caba project out near kind of where Interstate 40 and Highway 93 come together. There's the encouragement from that, and more recent drilling that's been done there. Just a quick review of what we've seen up on the Perseverance project. Chalcopyrite, bornite, potassium feldspar envelopes, D veins cutting porphyritic rock that's dated as laramide in age. Again, the same age as what we've drilled at Big Sandy, 72 to 74 million years. So we just haven't found the sweet spot at either one of them, but we're awful close, I think. A little bit of gold and some chrysocolla and a lot of leached capping out at Perseverance. These are the kinds of things that got Cordoba Minerals, Robert Friedland's group, interested and eventually taking an option. So they've got it. The steering wheel is in their hands. Bill wishes them good luck and Godspeed, and I wish they would get after it. They've also got big MT anomalies. Slide 29 now. So the kinds of electrical anomalies that we've found and drilled at Big Sandy with positive results are present out there at Perseverance. And I'd sure like to find the twin of what we found at Big Sandy at Perseverance. And that is the end. And I appreciate the opportunity to talk tonight. Again, it's an honor and a privilege, and I look forward to any questions that you might have. Thank you.
Hey, Tim, thanks so much. That was excellent. There are some questions in the chat. Do you want me to hand them off to you, or can you see them? You should be able to find the chat down below at the bottom of the screen.
If I scroll up to the top or down to the bottom?
Up towards the top, but the first 3 or 4 really not questions. I think the first one comes in around 6:59 from Scott.
659 Mansky. Any coarse grained white mica Grisen? No Grisen. Everybody's hearing me, huh?
Yes.
Scott, no Grisen in the drill core. Lots of Grisen back in the footwall. Some really spectacular Grisen. Centimeter scale muscovite flakes forming essentially pegmatitic sericitic envelopes. They're like giant D veins. If you could look under a microscope and look at D veins, this is what these Grisens back in the Diamond Joe stock and the Wheeler Wash stock look like. Very coarse Grisenous muscovite as envelopes on pyrite centerline veins. This is Peter Domes. Where's the water table in each of the 3 holes? It's very near the surface. Really, the first hole I drilled at Big Sandy, or that Godby drilled for me, wasn't an exploration hole. It was a water well, and I would recommend that to anybody out there exploring in Arizona, you might be better off drilling yourself a water well from hole one rather than spending a lot of fuel, diesel fuel, hauling water from miles away. But we hit water 65 feet below surface in our water well on the east side of the Big Sandy. The other holes we haven't, we've drilled those with mud, so we don't know the water levels, but it's very shallow. Mansky. The tilt on the system, the best evidence I got from tilt on the system is by doing spear tests as we went down BS3. I tried a couple of times to get a downhole televiewer, but the logger wasn't happy with the condition of the hole. But by spearing the inclined core, I was able to measure bedding angles. The steepest angles I measured were up to 42 degrees. Yeah, west-southwesterly is what I think the dip is. So, and it fans. It's only 12 to 15 degrees at the surface, and it fans westward, getting steeper, closer to bedrock, to a maximum of about 42 degrees. And Eugene Schmidt, that is a sunrise, not a sunset. Thorny Rogers, the pros and cons of MT. The frequency of the signal is so low that the depth of penetration is very great, many kilometers. Just by sitting on the same station and observing for literally days, you can get depths of investigation of tens of kilometers, even hundreds of kilometers. They study the mantle with magnetotellurics, and so it's depth of penetration that's really the advantage of magnetotellurics. IP wouldn't have shown us, and hasn't. I've actually done some IP out there now. 600, 700, 800 meters depth of investigation. You wouldn't have gotten down to sulfides at Big Sandy. Where is Perseverance? Where is the deposit? I wish I knew, but it's pretty close to the intersection of Highway 93 and Highway 40. About 15 miles east of Kingman. I answer to Tony's question, could it be mined in situ? I hope so. At least the very basic test, if you grind up and throw it in a jug of acid, will the chalcocite dissolve? Yeah, plus 96% of the copper goes into solution. If you do that, you don't get moly, you don't get rhenium, you don't get silver. Maybe that's okay. Maybe that's the best thing to do, is just go and get that copper. But what I'd like to do is find a sweeter spot and justify going down and getting everything. I might have skipped some there. John Ward, what are Bell's plans? Plans are to go find a giant porphyry copper deposit and get stinking rich. And that's sooner than later. I think the general structural setting. Yeah, I would say there was probably a single important fault that's roughly the east face of the Wallapai Mountains. There's been a bit of tilting, but man, when I can see bedding angles, even up at Perseverance as deep as the basement, Perseverance isn't tilted more than 20, maybe 25 degrees. Big Sandy seems to be a bit more in the low 40s. It's not a Urington kind of situation where the hanging wall is rotated 90 degrees by multiple stages of faulting. There's certainly multiple stages of faulting, but I think the faults, as they rotate a little bit and slip a little bit, they get a lot slipperier, and that coefficient of friction drops well below intact rock coefficients of friction, and I think things end up sliding a lot further. That was an acceptable answer 40 or 50 years ago, and became kind of unacceptable. But well, if you go and you look at natural systems where extensions taking place, I think there's good evidence a lot of places that these faults can move a long way at a very low angle, aseismically, and generate a lot of slippery clay in the process, and things can move a long distance. And really, that's what I think I'm finding. I'm finding the Diamond Joe system 13 kilometers away without 90 degrees of rotation.
Mm-hmm.
Brad Johnson, the Wallapai fault, I drilled it. I'm quite confident of it. up at Perseverance in my first hole. It was very bold. 1 mile east of the range front fault. I drilled 2,600 feet of gravel and drilled through a fault a couple of meters thick, and it was dipping at about 30 degrees at that location. So a couple of meters thick of fault gouge, gravel right on top of Precambrian. Looks like it's slid a long ways, slipperier than heck. You can see nice lineations in it that suggest which way it might have slipped, but a painfully obvious big fault. That's what it looks like. But if you go back in the wallop eyes around the Diamond Joe stock, I've never seen it at Diamond Joe. There's a couple of water wells that have been drilled through it. You don't get much of a feel for what the fault looks like from the water well cuttings, but it's roughly where you start seeing laramide fragments sticking out of the ground, adjacent to big boulders from the old alluvial fans.
Mhm.
I don't see any more questions after Brad Johnson.
I don't either. You know, what we can do, Tim, is if you'll stop sharing your screen, we can get a look at everybody and see if people have questions that they want to unmute themselves and ask.
Good.
All right.
Did you find that you had enough exotic copper to maybe make a small pit in that material?
I have not seen any place, a very small pit. I haven't seen any place where I would want to think about that yet. If you got a backhoe and a pickup truck, you could dig most of these occurrences out.
Tim, I got a question for you. That copper oxide, the leach cap that you've got there, is any of that just transported oxide, or is it all leach cap in place?
I think it's mainly indigenous iron oxide derived from sulfides that used to be there, chalcocite and pyrite.
Okay.
Tim, George Morgan.
Hi, George. How you doing?
Yeah, doing fine. I see you're doing fine. Good talk. I assume the fault you've got there is what we used to call the Lake Ranch Road fault.
Yeah, you bet it. And it's the one that it's in a GSA abstract that we called the Wallapai fault.
Okay.
Tim, I've lost my monitor, so I'm lost in the dark here. That was really excellent. Are there any last questions before we let Tim go?
Great.
Hey,
Thank
thanks
you very
so
much again.
Yeah, thank you so much, Tim, for doing that. That was excellent. Thank you, everybody, for joining us this evening.
Thank you for doing this.
Thanks very much.